Two locomotives that look nearly identical, hauling the same freight side by side, yet built on completely opposite engineering principles. And the mystery of why American railroading split into two rival camps. General Motors provided the springboard for electromotive diesel, or EMD, to revolutionize how goods moved across the continent. Beginning with a strategic acquisition in 1930, General Motors poured its massive automotive production expertise and research capital into the young enterprise, transforming it into an industrial powerhouse. By the middle of the 20th century, EMD locomotives had successfully broken the stranglehold of steam, making the brand synonymous with the very concept of freight diesel power. For generations of railroad workers, EMD represented the default standard of American railroading, known for simple, reliable machines that just worked. General Electric built its locomotive business through a completely different industrial path. General Electric did not step into the mainline market overnight. For decades, starting as early as 1907, the company established its reputation as a primary component supplier. It manufactured the heavy electrical systems, traction motors, and generators that powered locomotives built by other legacy builders, most notably Alco. Only later did General Electric step forward to engineer and assemble complete road locomotives under its own name, drawing on its decades of experience with heavy electrical engineering to challenge the established order. As other historic builders fell by the wayside, these two firms came to define the modern North American freight locomotive market. They established a dominance so complete that the comparison to Boeing and Airbus in commercial aviation fits the sheer scale of their rivalry. For decades, any railroad looking to acquire new mainline power faced a simple, unavoidable, binary choice. Buying locomotives meant choosing between these two names, committing a railroad's capital, maintenance shops, and crew training to one of two competing philosophies. That choice dictated everything from shop floor practices to the sound of the trains pulling heavy tonnage over the mountain passes. It was an industrial rivalry that split the rails of North America right down the middle, forcing railroads to pick a side. At the heart of this industrial division lies a fundamental difference in how these massive machines breathe and generate power. Every diesel engine operates by compressing air inside a cylinder until it is hot enough to ignite fuel. But the mechanical cycle used to capture that explosion splits EMD and GE into two opposing engineering camps. EMD committed to the two-stroke diesel cycle. In this design, every single downward stroke of the piston is a power stroke. The engine completes its entire cycle, intake, compression, power, and exhaust, in just one revolution of the crankshaft. Because the piston must perform all these tasks in a single cycle, it cannot rely on traditional valves alone. Instead, as the piston reaches the bottom of its stroke, it uncovers ports in the cylinder wall to let fresh air in, while mechanical valves in the cylinder head open to let exhaust out. A powerful mechanical blower forces fresh air into the cylinder to sweep away the burnt gases. This process, known as scavenging, means the engine fires twice as often as a four-stroke at any given speed. The result is rapid acceleration and high power density, giving EMD locomotives an immediate heavy pulling force that crews can feel the moment the throttle is opened. GE built its legacy on the four-stroke cycle, the same sequence found in most automobiles. Here, the engine requires two complete revolutions of the crankshaft for every single power stroke. The piston dedicates individual strokes to intake, compression, power, and exhaust. This separation of tasks requires a complex overhead valve train to precisely control the flow of air and exhaust, while a four-stroke fires half as often. Spreading the mechanical work across two revolutions allows the engine to breathe far more efficiently. The expansion stroke can be longer, extracting more energy from every drop of fuel and leading to superior thermal efficiency. This mechanical divide shaped the entire design of the locomotives. The two-stroke cycle offered mechanical simplicity, with fewer moving parts, but it demanded continuous mechanical air pressure to breathe. The four-stroke cycle traded that simplicity for a highly controlled combustion process, laying a foundation of efficiency and clean operation. In 1938, Locomotive introduced the 567 diesel engine on its landmark FT demonstrator locomotive, setting the template for mainline dieselization. Each cylinder displaced 567 cubic inches, utilizing an 8.5-inch bore and a 10-inch stroke. This Uniflow scavenged two-stroke design was built around a radical maintenance concept, the modular power assembly. Instead of tearing down an entire engine block to fix a single bad cylinder, EMD engineered a self-contained unit consisting of the cylinder head, liner, piston, and connecting rod. Shop crews could pull and replace an entire power assembly in a few hours with basic tools. This design philosophy prioritized locomotive uptime, turning local maintenance shops into highly efficient assembly lines, and establishing a culture of mechanical self-reliance across North American railroads. As tonnage demands grew, EMD scaled this exact layout. In 1965, the company launched the 645 series, keeping the same external engine frame but widening the cylinder bore to 9 inches. This engine powered the SD-42, a locomotive that became the workhorse of the industry due to its predictable performance under heavy load. By the mid-1980s, the lineage evolved into the 710 series. EMD kept the 9-inch bore but lengthened the piston stroke to 11 inches, increasing individual cylinder displacement to 11.6 liters. A 16-cylinder version of the 710 G3A prime mover, running at a maximum of 900 revolutions per minute, delivered 4,300 horsepower and a massive 25,100 pound-feet of torque. This mechanical layout produced a distinct operational character known in the industry as first-notch power. Because a two-stroke engine fires on every single crankshaft revolution, it does not suffer from turbo lag when moving from a standstill. The moment an engineer opens the throttle, the engine delivers immediate torque to the traction motors. Railroad crews operating heavy tonnage relied on this instantaneous response to start massive trains on steep mountain grades without slipping their wheels. To feed air to the cylinders at low speeds, EMD utilized a gear-driven roots blower, or a clutch-assisted turbocharger that remained mechanically coupled to the crankshaft until the engine reached higher revolutions per minute. This mechanical forced induction system gave EMD locomotives their iconic, deep drumming chant. For decades, maintenance foremen preferred this mechanical straightforwardness over electronic sophistication. Diagnostics were physical, not digital. If a locomotive suffered a power loss, shop crews did not rely on software fault codes. They opened the side crankcase inspection covers, physically inspected the cylinder liners, and checked the fuel racks by hand. EMD's design culture prioritized rugged, thick-walled steel components and gear-driven accessories over delicate control systems. This brute simplicity cemented EMD's position as the bedrock of American freight railroading, creating a generation of railroaders who believed that if a machine could not be fixed with a wrench and a hammer on a siding, it did not belong on the tracks. General Electric approached the tracks by viewing the locomotive as an integrated electrical grid. Because the company spent decades manufacturing traction motors, generators, and control systems for other builders before assembling complete locomotives, its engineering culture focused on electrical efficiency and system-wide control logic. This component supplier heritage meant that when General Electric began building its own road locomotives, it did not mimic EMD's mechanically focused design. Instead, General Electric treated the diesel engine as one part of a complex managed network. This alternative philosophy prioritized thermal efficiency and fuel economy, while EMD built two-stroke engines for immediate torque. General Electric utilized the four-stroke cycle to extract the maximum amount of work from every drop of diesel. The four-stroke design allowed for a longer expansion stroke and more precise air-to-fuel ratios, which naturally lowered specific fuel consumption. It also kept peak combustion temperatures lower, providing an inherent advantage in reducing exhaust emissions. For railroads calculating operating expenses over millions of miles, General Electric's focus on squeezing fuel savings from the combustion cycle became a major selling point. The true differentiator in General Electric's philosophy, however, was the introduction of advanced electronics and diagnostics. While EMD locomotives relied on physical inspections and mechanical simplicity, General Electric began wrapping its prime movers in layers of microprocessors and sensors. Computerized control units monitored critical parameters, including exhaust gas temperatures, fuel injection timing, and turbocharger pressures. This digital architecture shifted the maintenance paradigm. Instead of waiting for a part to break physically, onboard diagnostic systems identified performance drops and logged specific fault codes. Maintenance became a matter of software updates and component monitoring, allowing railroads to anticipate failures before they occurred on the main line. This electronic culture reached maturity with the development of alternating current, or AC, traction. Managing AC traction motors required highly sophisticated electronic inverters and complex computer algorithms to prevent wheel slip. General Electric's decades of heavy electrical experience allowed them to integrate these technologies far more effectively than their competitors. The company invested hundreds of millions of dollars over nearly a decade of research to refine this integration, culminating in the Evolution platform. By pairing a high-efficiency, four-stroke engine with precise electronic control of individual axles, General Electric created a machine that could pull heavy tonnage with remarkable efficiency and minimal wheel spin. Ultimately, General Electric's philosophy treated the locomotive as a managed system. The machine was designed to be monitored continuously, optimized electronically, and run at peak thermal efficiency. This analytical systems-first approach shifted the industrial standard away from mechanical ruggedness toward digital precision, redefining what a modern freight locomotive could achieve on North American rails. The fierce competition between Electromotive and General Electric was a product of massive industry consolidation. Originally, the North American market was crowded with specialized builders. Steam-era titans like Baldwin, Lima Hamilton, and the engine maker Fairbanks Morse all fought for a share of the rapidly dieselizing market. By the mid-1960s, these legacy builders had collapsed, leaving only a handful of viable competitors on the high iron. The concentration of market power into a total duopoly occurred because of the decline of the American Locomotive Company, widely known as ALCO. Based in Schenectady, New York, ALCO was Electromotive's most formidable mid-century competitor, using high-performance four-stroke diesel designs. But ALCO struggled to maintain market share against General Motors' manufacturing might. By 1969, ALCO officially exited the locomotive market entirely, closing its doors and leaving railroads with fewer options. As ALCO retreated, General Electric stepped into the void. Having spent decades supplying electrical components to ALCO, General Electric acquired many of the defunct builder's remaining assets, engineering talent, and technical designs. This acquisition, which included elements of ALCO's 251 engine line, provided General Electric with the mechanical foundation it needed to change from a component supplier to a builder of complete road locomotives. When the dust settled from this industry-wide consolidation, the alternative choices for Class I railroads had vanished. Every other builder had run out of road. Electromotive and General Electric stood alone as the only manufacturers capable of delivering a complete, high-horsepower mainline locomotive package, splitting the rails between them. The historical balance of power broke apart at the turn of the century. For decades, EMD maintained the larger share of the mainline fleet, but the early 2000s brought a clear turn in market momentum. This change occurred because of EMD's mechanical missteps and GE's development of alternating current traction. In 1995, EMD attempted to win the high horsepower race by introducing the SD9E Mac. Designed to deliver 6,000 horsepower from a newly engineered 20-cylinder H engine, the Locomotive instead suffered frequent mechanical failures. Pistons, connecting rods, and cooling systems failed in the field, forcing railroads to downgrade the units or pull them from service entirely. This expensive crisis severely damaged buyer confidence in EMD's pipeline. GE met this moment by focusing on tractive adhesion rather than raw horsepower. Their AC4400CW and later the 4-stroke Evolution Series ES44AC used computerized wheel slip control to deliver superior pulling force on heavy haul grades. While EMD's complex H engine faltered, GE's 4-stroke platform offered predictable operating economics and lower fuel consumption. The change in purchasing patterns was rapid. In 2005, BNSF placed a massive order for GE's alternating current locomotives, followed by CSX, initiating a phased acquisition program. By the middle of the decade, GE's annual delivery volumes surpassed EMD's for the first time. It was not a sudden collapse for EMD, but a quiet, steady migration of capital. Railroads realized that GE's electrical systems and reliable alternating current traction delivered better ton-mile economics, permanently tilting the balance of North American railroading. When a Class I railroad acquires a new locomotive, the purchase price represents only a fraction of the long-term investment. Railroads buy a complete maintenance universe. Every locomotive represents a multi-decade commitment to a specific mechanical and electronic ecosystem, creating a powerful network effect that makes switching brands an incredibly expensive and logistically punishing decision. At the center of this industrial lock-in are proprietary parts. EMD locomotives require specialized components like D43 traction motors, while GE units rely on systems like B30 inverter packages. Because a locomotive earning thousands of dollars an hour cannot sit idle waiting for a delivery, railroad maintenance departments must stock thousands of individual parts. A single major shop floor holds extensive inventories of these specialized components, from individual cylinder assemblies to electronic control cards, representing millions of dollars in capital. Swapping to a competing builder means writing off this inventory or maintaining two entirely separate, highly redundant supply chains. Beyond the hardware, the human factor solidifies this division. Maintenance crews and operating managers spend decades learning the specific quirks, diagnostic routines, and repair procedures of one system. In an EMD shop, a cylinder head change is a physical routine built around modular power assemblies. In a GE shop, diagnostics are driven by software and microprocessors. Introducing a new locomotive type with a fundamentally different engineering philosophy disrupts these established routines, requiring extensive retraining and introducing costly errors during repairs. Ultimately, the total ownership cost of ownership dictates purchasing logic. The cheapest locomotive on paper is rarely the cheapest one to live with. If it forces a railroad to rebuild its shops, retrain its mechanics, and restock its shelves. Operational familiarity and parts compatibility outweigh minor differences in initial sticker price. This is where brand preference turns into permanent industrial dependence. The regulatory environment of North American railroading fractured in December 1997. The Environmental Protection Agency adopted the first tiered emission standards, establishing a multi-decade roadmap that transformed locomotive design from a performance race into a compliance battle. Tier 0 through Tier 2 standards took effect in 2000, followed by the Tier 3 rule finalized in 2008, which became active in 2011 and 2012. These rules steadily reduced allowable levels of nitrogen oxides and particulate matter, forcing both builders to alter how their engines managed combustion. The definitive technical barrier arrived in 2015 with Tier 4, a standard requiring a 90% reduction in particulate matter and an 80% reduction in nitrogen oxides compared to previous limits. This strict regulatory timeline exposed the physical limits of the two-stroke diesel cycle. A two-stroke engine lacks dedicated intake and exhaust strokes, relying instead on high-pressure air scavenging to push spent exhaust from the cylinder. This configuration leaves no physical room for a dedicated exhaust gas recirculation loop, the primary method used to lower combustion temperatures. At the same time, the two-stroke's shorter exhaust gas residence time reduces the operating window and chemical effectiveness of selective catalytic reduction systems. EMD engineers struggled to fit these massive subsystems into their traditional frame dimensions. To meet Tier 4 with the two-stroke 710 engine, Progress Rail had to design a sprawling, external exhaust aftertreatment assembly. The resulting SD70 ACT4 required a complex arrangement of urea-based selective catalytic reduction and diesel particulate filters, mounted on top of a modified, heavier chassis. This arrangement added weight and introduced immediate heat management issues, resulting in early mechanical failures during revenue service. GE, conversely, had constructed its platform around a four-stroke design. The four-stroke cycle, with its separate dedicated intake and exhaust strokes, was highly compatible with exhaust gas recirculation and precise valve timing. GE engineered the Evolution series from the outset to accommodate emissions hardware and advanced digital control software. The onboard processors continuously adjusted fuel injection timing and exhaust routing to manage combustion temperatures in the cylinders. GE met the Tier 4 limits with fewer mechanical compromises, expanding its market advantage and leaving the two-stroke philosophy fighting for its survival on the modern mainline. A 2024 industry survey of Class 1 maintenance managers recorded a mean time between failures of roughly 1,200 hours for General Electric Evolution units, compared to about 1,050 hours for EMD 710-powered locomotives. While these statistics suggest a slight operational edge for GE, raw uptime numbers tell only part of the story. Real-world dependability is shaped by how a locomotive fails and how long it remains out of service. In an EMD-dominated shop, a mechanical failure is a physical problem. Mechanics can swap a modular power assembly in a single shift with standard tools, keeping the engine's off-track time predictable. With GE, the troubleshooting is digital. Onboard microprocessors pinpoint faults instantly, but if an electronic card or a traction inverter fails, the locomotive must wait for proprietary parts. A high-efficiency machine sidelined by a software error is just as idle as one with mechanical damage. This difference in diagnostic turnaround changes how railroads experience downtime. As a result, long-term shop logs from railroads like Union Pacific do not produce a single, universal victor. One maintenance hub might show EMD units handling rugged branch line service with minimal electrical faults, while another records GE units logging superior mileage on long-haul intermodal routes. The two builders simply measured different kinds of reliability, one built on physical simplicity, the other on software precision. Because the data changes with every route and maintenance team, the debate remains open. The mechanical and electrical systems of these competing platforms ultimately outlived the corporate independence of the companies that designed them. EMD entered a new corporate era in 2010, when Caterpillar's rail subsidiary, Progress Rail, acquired the historic builder for $820 million, with an additional $108 million working capital adjustment. 9 years later, General Electric reshaped its own industrial footprint. In 2019, GE Transportation merged with Wabtec Corporation through an $11.1 billion reverse Morris Trust transaction. Rather than introducing fresh competition to the high iron, these acquisitions concentrated the market even further. The decades-old rivalry did not disappear. It was simply absorbed into larger corporate portfolios. Today, the legacies of EMD and GE are preserved inside these two corporate umbrellas, which together account for roughly 3/4 of the active freight locomotive fleet in North America. The market has shifted from a multi-builder race into a highly managed duopoly. Railroads seeking mainline power no longer choose between scrappy, independent inventors, but instead rely on a tightly structured aftermarket and new build market controlled by just two massive suppliers. The mechanical battle lines remain, but the corporate field has narrowed to a permanent structural lock. In 2023, the corporate rivalry entered the United States District Court for the District of Delaware. Progress Rail filed an antitrust lawsuit against Wabtec, transferring the competition from the high iron to the courtroom. The legal dispute centered not on who built the best new locomotives, but on who controlled the aftermarket parts needed to keep active fleets moving. Progress Rail alleged that Wabtec used its acquisition of GE Transportation to monopolize the parts supply, engaging in tying arrangements, refusal to deal, and extreme pricing pressure. The court filings detailed allegations that Wabtec inflated prices of GE-derived components by up to 30% above historic benchmarks. The suit also claimed that Wabtec forced Class I railroads into bundled service contracts, requiring them to purchase complete systems when only a single component was actually needed, which locked out independent rebuilders and escalated operating costs. The legal pressure culminated in a settlement in February 2026. Without admitting wrongdoing, Wabtec agreed to terms that required the company to offer non-exclusive access to specific parts and banned them from tying unrelated services to parts sales. The settlement avoided a final trial, but the battle proved that when a market is this concentrated, competition moves from technical engineering on the tracks to the legal control of everyday maintenance. The active North American freight locomotive fleet stood at 37,593 units at the close of 2025, but this massive pool of machinery is largely static. In 2023, only about 200 new or rebuilt locomotives entered service across the continent, a steep fall from the historical replacement pace of 500 units per year. Uncertainty over future electrification mandates and caution surrounding freight cycles have forced railroads to delay major capital purchases. Instead of ordering new locomotives, operators are stretching the operating life of existing assets. This shrinkage changes the nature of the industrial rivalry. With new sales scarce, the battle is no longer won on assembly lines, but in maintenance bays, aftermarket parts, proprietary component support, and life-extending rebuild programs now generate the bulk of the revenue. The engineering competition between EMD and GE remains, but it survives within a much thinner arena, where maintaining legacy fleets takes precedence over building new ones. We have reached the end of the mechanical divide. Today, the pressure to decarbonize is rewriting the rules of heavy freight. The question is no longer which diesel engine wins, but who powers the zero-emission future. As the tracks ahead change, this century-old rivalry remains far from settled. Which philosophy do you think will survive? Let us know in the comments.